So, okay, language-wise, okay, the way your bell ringer is worded, we're talking about something that is intramolecular versus something that is intermolecular. What does intra versus inter mean?
Well, intra would not be like within the molecule.
Intra is within.
And then inter would be outside. Or would be
So, like, what is an inter state? Tyler?
between.
Okay? So, and those are really, really important distinctions. What we have done up to this point is dealt with intramolecular bonds. Okay? So if you have something like water, okay, these bonds inside water are intramolecular bonds. Ionic, polar covalent, non-polar covalent. What we are going to do, and this dictates so many of the properties that we're going to talk about going forward. This is a day where you have to stay on. So Lauren, you said you're going to have trouble, like, if you have to, get up, walk around. Okay? Stay awake. Okay? So, what's different now is now we're talking about how particles interconnect. Okay? So intermolecular forces are the forces between neighboring molecules. So these two waters, an intramolecular bond is the bond between two molecules within the atom. Intermolecular forces is how a water and another water stay connected. Okay? And there's several layers of this. So, okay, at the top it says intermolecular forces. Okay, you may also refer to them as interparticle forces or IMFs. I will tell you, okay, an IMF, okay, is a common enough abbreviation that you could probably use it on like the college board exam and you'll be fine. Okay, they'll know what that means. Highlight where it says the bonds that hold atoms together in molecules are similar to those that hold molecules together. Now, there's a hierarchy. Okay, there's a triage of 3 in a top tier, okay, and then 3 in a lower tier. So the first set are 3 types of intermolecular bonds. Okay? So these are bonds that are exactly the same as the bonds within molecules, and that's why they're so much stronger. So these 3 are your strongest. Now, I would write somewhere. Okay, the strength of your intermolecular force directly influences the physical properties of a substance. Okay? So for example, okay, Garrett and Clayton, let me use you for a second, please. Would you stand? Okay, come over here, just, come over here, just so we have some room. All right, here's what I need you to do, okay? Grab hold of his arm. You don't have to, it was weird you guys went straight to the hug, guys. Okay, so, okay, just grab hold of his arm, okay? So now, as a solid, okay, they're directly linked. Okay, when we go to turn a solid into a liquid, what do we have to do? We gotta heat it. What does that do to the particles? Makes them speed up, makes them move, okay? So now, instead of being really tight, they get a little bit more spread out. Okay, and now, how do we go from a liquid to a gas? Heat them more. Now they're flying all over the point until we break that interaction. Okay, so solid, nice and tight, strong together. So things that are solids have really strong forces. It's if Garrett had a strong grip, like a boy almost. Okay? Come on, nobody got me. Come on, that was funny. Like if you had him.
Nice try though, buddy.
What?
Anyway, okay, so Garrett being able to hold on to him with a strong grip is like a solid. Okay, the further he gets away, the less his grip is, more like substances that would exhibit a liquid, weaker intermolecular forces. The fact that he can't hold on because he's being moved too fast, okay, that's going to give you a weaker attraction, and most of those things will be gases at room temperature. Okay, so if we look at some of the elements on the periodic table, some of the compounds that we know, they are solids, liquids, and gases at normal temperatures because of these intermolecular forces. Okay, so for example, we're talking about things like melting point, boiling point, solubility, okay, some of those things. Okay, so under ionic, okay, we've talked about ionic bonds. How do we know if something is ionic? Metal and a non-metal. Okay? Ionic solid is held together by electrostatic attractions. What was the other word that we use for electrostatic? Coulombic. Okay? These are governed by Coulombic attraction, right? And in turn, Coulomb's law. Okay? Now, electrostatic attraction, Coulombic attraction were just fancy ways of saying what? Oh, come on. It means opposite charges attract. Okay? Think about an ionic bond. You've got a cation and an anion. The linkage for those two things is simply the attraction of those charges. Okay? So, where it says, the same attraction that holds ions together in a molecule, our formula unit of NaCl, is the same that holds a block together. Okay, so if we're looking at an ionic crystal lattice, okay, what happens here is each charge is surrounded on all adjacent sides by the opposite charge. It locks them in place. There's no orbital overlap, which means that there's no actual exchange of electrons. It's just the magnitude of positive and negative that keeps them together. Okay, so this would be more like what your lattice looks like. Now, the ionic lattice is very, very strong. Okay, each yellow is surrounded on the adjacent, on all adjacent sides by the green. However, there are planes that allow the ionic crystal to be fractured. Okay, so it does have a little bit of brittleness to it. Okay, you can see it maybe a little bit easier here. Okay, we can fracture those planes between the layers. Okay, so it says ionic bonds are strong and substances held together by them have high melting and boiling points. So any of these three, okay, are going to be pretty strong. Highlight where it says ionic bonds are poor conductors of electricity. And then highlight the star right underneath it. Each electron is localized around a particular atom, so the electrons cannot move within the lattice. I think we talked about that when we talked about like the bond itself, right? Okay, we talked about the term delocalized. So when water gets involved here, the dipoles that water has, because it's superpolar, is able to interrupt this attraction of positive to negative, split them apart. Once those ions become mobile, so do the electrons, and allows the electricity to be conducted, but only when it's in solution, not as a solid. All right. So, look down at network covalent. So, the exact same structure that holds ionic molecules together in a lattice holds network covalent molecules together in a lattice. The lattice is just different. Okay? So, the lattice is now connected with covalent bonds. That is really cool. Maybe that's why. Okay, so you get a lattice, okay, an aggregated structure of covalent bonds. Okay, now if you notice, these are typically much harder substances. Okay, diamond is an example. What do we know about diamond? Super hard, right? It's the hardest natural substance we have. Here's the reason why. The ionic substances, remember, have those layers where we can fracture them. Okay, here's what the internal structure of diamond looks like. Okay, do you see any planes where you can fracture something consistently? Okay, so if you fracture it here, okay, you might be able to chip it, okay, but then there's aggregated structures underneath almost supporting that angle. Okay, so diamond is an example. Okay, so there's not really a good, like for example, this is metal and non-metal. This one you just kind of have to remember examples. Okay, so diamond, quartz, which is silicon dioxide, SiO2, and then like aggregated nonmetals. Okay, so the nonmetal like solids. So when we find phosphorus elementally, it's usually P5. Sulfur is S6 or S8. Okay? Most of your nonmetals, okay, are gases. So there's only a few of these that'll be an example. So the most common that you'll see are going to be diamond and quartz. Those are the most common that have been on the exam in the past. Okay, now, okay, they are held together by a lattice of covalent bonds, similarly to ionic, except instead of that Coulombic attraction, it's now actual electrons being shared through an overlap of orbitals. Highlight that third line. These are poor conductors because the electrons are localized and they are not free to move. Okay, and then we talked about the examples. The third are metallic bonds. Okay, and these are typically metals by themselves or alloys. Okay, what's an alloy? A mixture of metals. Okay, so for example, white gold, okay, is a mixture of either silver and gold or like platinum and gold, right? Nickel cadmium is an alloy, okay, that's used in a lot of like watch batteries or calculator batteries. Okay, so an alloy is just a metal mixture. But if like a metal by itself, if you have a sample of copper, a sample of iron, a sample of sodium, they will all exist this way. Okay, highlight where it says they are a group of nuclei surrounded by a sea of mobile electrons. Okay, so for example, copper is one of the most conductive substances we have. Okay, think of copper ions as like two islands in an ocean. And in that ocean, instead of piranha, we have electrons. Okay? That sea of electrons means that those electrons can essentially flow wherever they want. Back and forth between the ions, okay, in the space between them, they can go pretty much whatever they want. Those mobile electrons essentially represent all of the properties that we know exist for metallic bonds, okay, or for metals. What do you know about metals? They're good conductors, okay? So let's talk about that. If they conduct electricity, electricity is a flow of what? Well, it's a flow of energy, but what is the energy? Electricity. Electrons, okay? Electrons are moving back and forth, right? Okay? It's also a conductor of heat. Well, the more movement you get, the more particles slide past one another. Do me a favor, put your palms together, rub them back and forth, nice and fast. What do you feel? Hey, feel heat. Friction builds heat. The more particles that are moving back and forth together, as long as there's a point charge supplied, gives you heat. Okay, what else do we know about metals? Look to the back. Look at the spouts of the six. They're shiny. Okay. Well, we know because of Max Planck and Einstein, okay, that light and electrons are very, very similar, right? So when light hits, we inject it with energy. Because of their similarities in energy, the electron gets ejected off, right? That's the photoelectric effect. It's why metals are shiny, okay? We look back, we see the light reflecting off, because as that light essentially excites the electrons, it does enough to eject it from the surface. Okay, so that mobile sea of electrons allows things to be a little bit more shiny because there's more electrons. So, they're also malleable and ductile. These islands are easily movable once you heat it up and essentially liquefy the metal. It's then able to dry and reposition. Okay, so that's second line. Free moving electrons make them malleable and ductile. And at the bottom, good conductors of heat and electricity because the electrons are delocalized and can move freely throughout. Okay, so that's hierarchy number one. Okay, and there might be some ways to break some ties here. Okay, the tie you would have to break with this one is Coulomb's law. We did that a little bit when we talked about ionic bonds before. What do you know about Coulomb's law? What are the two things that it's dependent on? If you don't know, page back to where we talked about ionics. Chase. Distance and charge. Okay, and is that the right order? What matters more? Charge matters more, okay? So, charge only because its magnitude typically in whole numbers or in multiples The distance doesn't matter as much simply because you're usually comparing like a 10th decimal place, a nanometer or a picometer. Okay, so the difference between 1 nano and 1 picometer, something like that, is obviously much smaller than the difference between the number 1 and 2. Okay, so charge and distance. We'll talk about how to answer these questions here at the end. Now, these last 4, or these last 3, all fall into the category of what are called van der Waals forces. Okay, now I will tell you, you probably are not going to hear that term from me a ton, because we really treat them separately. Biology, if you've taken AP Bio, you've probably heard that term, but they group all of these together. These are very distinctly different. Okay, now, number 4 is a hydrogen bond. And contrary to what many biologists will tell you, it is not a bond. It is an intermolecular force. Okay, it is nowhere near as strong as a bond. But we are going to jump down. We're going to come back to hydrogen bond. We're going to jump down to where it says dipole-dipole forces. Okay, we're going to start there. Okay, and these are in a hierarchy now. So the top 3 kind of exist in a tier by themselves. You're not going to have to worry about breaking the tie between ionic and metallic. They kind of go in a tier by themselves. However, at the bottom, 4, 5, and 6 typically go in order. Okay? So, look at dipole-dipole. Highlight that first line where it says, occurs with polar molecules. Okay? And this is why we spend so much time on polar versus nonpolar. You have to be able to identify a polar or nonpolar molecule. Okay? So it says, this is where the positive end of one polar molecule attracts the negative end of the other. That was what I showed you earlier with the water. Highlight that line. Okay, highlight the next line where it says, the greater the polarity of the molecule means greater dipole-dipole interaction. So molecules with larger dipole moments essentially have stronger forces. Okay, so what do I mean by that? Well, let's say we've got something like HBr and HI. Okay? Now, I realize that we're also comparing this to a linear molecule, so we really are looking at bond polarity as well as molecular polarity. Okay? But between Br and H, or I'm sorry, between Br and I, which one is further away from H? I, right? So this should be a more polar bond. Okay? The electrons exist closer to I than they do in Br, correct? That means the magnitude of this partial negative is higher than the magnitude of this partial negative. So when another HI comes along, this interaction is going to be a little bit stronger than the one with HBr. Does that make sense? Okay? So then it says, this is a relatively weak attraction, so usually it melts and boils at low temperatures. And then most of these are gases or liquids at room temperature. Okay, so the most important part of this is the fact that we have polar molecules. Now, understanding what that is, now we jump back up to hydrogen bond. Highlight the first line because it is a supercharged dipole-dipole interaction. Okay, highlight the star. It only occurs H with F, O, or N. Okay, now it's H interacting with F, O, or N from an adjacent part of the molecule. Okay, now, so my teacher always used to say H only answers the phone for F, O, and N, if that helps you. Okay, if it doesn't, then just disregard it if you want to memorize it. Now, why is this a supercharged dipole? Well, what are F, O, and N? They are extremely electronegative. So they are really pulling these electrons closer, which means the magnitude of their partial charges go up. Okay, they are the 3 strongest dipoles that can be created with hydrogen. Okay, so when we're talking about the strength of HI or HBr, these three, HF or H2O or something with H and N in it, big time strong. Okay? So it's kind of the difference between having like kind of a decent grip and being latched onto something. Okay? Not as strong as a bond, but pretty close. Okay? Now it says, these are higher melting and boiling points in substances with regular dipole-dipole forces, and that's simply because the magnitude of those partial charges is higher. All right, number 6. This is called London dispersion forces. Okay? Now, you need to make a note here, and I should have probably put it in for you, and I didn't. Every substance has London dispersion forces. Every single one. They are usually overshadowed, though, by stronger intermolecular forces. So, for example, okay, something like NaCl, metal and a nonmetal, we would say has what type of bonding? Ashley? Ionic. That ionic bond also has London dispersion forces. They just don't matter because they're super, super weak, and because that ionic bond is a stronger presence. So, for example, okay, Garrett, stand up for me. Okay? Okay, so we're an ionic bond. Okay, so we're linked. Okay? Doesn't matter that I'm holding onto his shirt, okay, with a tiny grip, right? Because this linkage, pull away, okay, is so much stronger. He's gonna pull me with it. Okay? That extra pull that the London dispersion force would have is insignificant compared to the stronger force. Okay? Now, London dispersion occurred with all polar molecules. Dipole occurred with polar. This is with non-polar molecules and noble gases specifically. Now remember, every substance has these, but this is the only force that a substance that's non-polar or a noble gas has. Things that are relatively non-reactive. Okay? Yeah.
So you can pretty much distinguish the difference. If it is a polar molecule, it's going to be most likely dipole-dipole.
Correct.
Unless it's a hybrid or whatever.
Correct. That's exactly right.
And then if it's non-polar, it's going to be
right. And if it's any of the other four, it's going to be that and London dispersion. Right. Okay. And so they'll often ask you questions like, what is the strongest intermolecular force for blank? At which point, if it's NaCl, you would say ionic. Okay? If it asks you to list all of the forces involved, then you would also have to list London dispersion. Okay, now here's what London dispersion is. Okay, it says this occurs between non-polar molecules and is the only type for non-polar noble gases. Highlight that first line. Okay, and then the second line as well. It depends on random, instantaneous dipole moments. Okay? So, what do electrons do to each other? They repel. So, what happens is, Clayton's a non-polar molecule. Okay? Let's just say he and I are twins. I'm sorry. Okay? We are exactly the same. Maybe it's a CH4, a CO2, neon, whatever. Okay? He is a non-polar entity. When two non-polar entities get close enough together, just in passing, those electrons that are involved in that interaction essentially repel each other and get thrown throughout the molecule. When that happens for just an instant, we make eye contact, and then I go past, no more interaction. Instantaneous dipole moment. Okay, and then I'm running around the classroom, and I see Judd, instantaneous eye contact, electrons get flustered, instantaneous charge, and then we're away, everything goes back to normal. Okay? So, think about it you ever been in a room with the smelly kid? And the smelly kid walks past you and it's oh. And you turn, kind of the same thing. Okay? Smelly kid comes close, all the electrons get shifted, you turn away because you're repelled. Okay? And that's a London dispersion force. For that one instant, You're reacting to that external stimuli. Same idea. Now, these are super, super weak because they don't occur naturally. Okay? They only occur because of interaction. So imagine if you're dealing with a gas. What do we know about the particles of a gas? They're flying all over the place, right? So it's whenever those particles happen to come close together. And remember, particles are spread out. Okay? So it's only happening when they come close together, they link for a second, and then they pass. Okay? Now, that third star, since this is dependent on the random movement of electrons, molecules with more electrons experience greater forces and have higher properties. Super, super important. Okay, highlight that. Okay, it says these are weaker than dipole-dipole, so they melt and boil at very low temperatures, and most are gases. Okay, highlight the very bottom, because that word becomes a big-time buzzword here. Polarizability. So, those instantaneous dipole moments are dependent on the electrons in the movement. Okay? So let's say you're all electrons. Everybody stand up. Okay? And you're all electrons in the molecule of this classroom. Okay? And for example, you gotta imagine me kind of as a much bigger entity. Okay, but as I'm coming across, okay, we interact. You guys are all electrons inside a single molecule. Okay, I come, my electrons interact with yours. You guys all shuffle it that way. Everybody go to the wall. Okay, so since the classroom is a much bigger atom or molecule than my molecule, okay, all of the electrons get shifted to a much broader space. So now that end of the molecule becomes much more negative. Can we agree? This end of the molecule becomes much more positive. So as long as I'm interacting with it for that instant, we have an attraction. And then I leave the room, and you guys all go back to your seats. And it ends just like that. Okay? So the idea that this room is bigger means that the shifting can occur in a greater space. It creates a stronger partial charge for that instant, simply because the electrons can move. Now, it also talks about more electrons. If it was just Tyler and he moved, okay, would that create as strong a partial charge as with everyone? Because there's more electrons, right? More negativity. That's what polarizability means. It means as more electrons shift to a bigger space, it creates a stronger instantaneous charge. Basically, as the smell gets closer, you're more averted to it. Okay, it's kind of the application. Okay, so now we're going to talk about how to answer questions like this. Okay, so and I will say, if you remember in like Chem 1, I think we even talked about it a little bit earlier with this unit with periodic trends. There's certain question types where it's not wrong, it's just not enough. Do you guys remember mentioning that? So this is one where we've got to make sure there's enough information, okay? Because they're very particular about the way we do this. Okay, so for example, we are going to compare CaO and NaF. Okay, now, we've already done this, believe it or not. We did it back when we talked about ionic bonds. But now we're going to talk about it with a little bit broader knowledge base. Okay, so the example is going to be CaO has a higher melting point. Explain that interaction, or explain that observation. Okay, so how many of you have taken like AP Lit or AP Language? Okay, or an English class where you had to learn the structure of how to write like a 5-paragraph essay? Like 3 of you. Okay, so now I'm not asking you to write a 5-paragraph essay, but the structure here is very important. Okay, so number one, okay, we need to relate the property to our evaluation tool. And our evaluation tool here is strength of intermolecular forces. So, we say something like melting point is dependent on the strength of intermolecular forces. So there's our topic sentence. Okay, we have outlined what we are using as our evaluative tool. And I'm not asking you to list these. These will typically go in like a paragraph format. So now, we need to look at both of these molecules. Both CaO and NaF exhibit what? Megan, ionic bonding. Because, now we justify. Judd, why are they both ionically bonded? Not two different nonmetals.
It's a metal.
It's a metal and a nonmetal. Calcium and oxygen, metal and a nonmetal. Okay, so both are a metal, bonded to, I'm using with, you should probably say bonded to, a nonmetal. Okay, now, okay, so what did we say governs the strength of ionic bonds? Coulombic attraction. So when ionically bonded, properties are dependent on Coulombic attraction. Now you could say electrostatic attraction, you could say Coulomb's law, you could say any of the three. They all essentially are representing the same thing. Okay, so when ionically bonded, we now have to look at Coulombic attraction. CaO has what kind of charges? Plus 2n, plus 2n minus 2. And NaF has what? Group 1, group 17. So, Lauren, plus 1, minus 1 as their charges. Okay? Coulomb's law says that a higher magnitude of charge means higher attractive forces. You guys remember that? Chase, you said it was charge and distance. So if the charges were the same, then what would we rely on? Then we would rely on distance. Okay? So, now we wrap it up. CaO has higher charge, and therefore a higher melting point. Let's say attractive force. Okay, sorry. Okay, so now we got to look at what thorough means. Okay, thorough is we've tied the property to the evaluation tool. We've tied it to the strength of forces. Okay. Next, we've identified the forces and justified why we know that. Then we've talked about what breaks the tie since they're both the same. Now, if this had been, let's say, ionic and dipole-dipole, we would simply say ionic bonds are stronger interparticle forces than a dipole-dipole interaction, so it has a higher boiling point or a higher melting point.
Would we have to explain that, or is that just
No, that's understood. Okay. You know, this just has more explanation because you're breaking a tie. Okay. Does this make sense? Everybody okay? Okay. So now we're going to do the other kind of tricky one. Can I erase this? Or do you guys need to copy your? What's that? Okay.
So if they had like the same charges.
So great question. What if I gave you NaF versus KBr? Okay. So first thing we look at, both of them are what? Metal and non-metal. So we're going to follow the same formula. Melting point is dependent on the strength of intermolecular forces. Both NAF and KBr exhibit ionic bonding because metal and non-metal. Okay, so when ionically bonded, properties are dependent on Coulomb's law, Coulombic attraction, whatever. Now, can we use this? No. Our statement here is both of them exhibit +1, -1 charge differences, right? So then we have to look at distance between them, radius squared. Remember, Coulomb's law is attractive force is a positive charge times the negative charge over the radius, right? Now, which one gives us more attraction? Think about the fact that this is in the denominator. Close together, far apart. If radius is big, what does that do here? If it's small, what does that do here? Bigger radius means smaller attractive force, right? So we want two things that are smaller, okay? So instead of Coulomb's law starting at magnitude, we're going to say Coulomb's law states that smaller ions means a higher attractive force, right? So now we look. Where is sodium? Well, group 1 doesn't help us. Period 3. So it's got 3 energy levels, right? What about fluorine? I think it's 2, right? Okay. How about K and Br? They're both in the 4th energy level. So, since sodium and fluorine are both smaller ions than K and Br, they would have a smaller radius and therefore higher attractive force. Therefore, NAF would have a higher melting point. Does that make sense? Same formula, we're just using the information at hand. Okay? Hunter, are you okay? You caught up? All right. So now let's look at Ne versus CO2. Okay? Which has the lower melting point? Okay, so same formula, right? Now, these are totally different molecules. I would argue it probably doesn't kill you to draw the structure, okay? But you may not have to, and you can picture it in your head. First thing, okay, we relate the property to what we're dealing with, okay? Lower melting point means what? Less or weaker IMFs. Okay, so we tied it to, there's our topic sentence. Lower melting point means we have weaker intermolecular forces. What does neon do? Let's think about it. Is neon a metal and a non-metal? Can't be ionic. Is it one of the examples for network covalent? Can't be that. Is it a metal? Can't be metallic. Is it H bonded with FO or N? We're not doing so hot. Okay? Is it a polar molecule? Okay? So what's it have to be? London dispersion. Exhibits London dispersion forces because it is a gas. CO2. What's CO2 look like? C. Double bond O's. What does CO2 do? Is it a metal and a non-metal? Is it one of the network covalent examples? Is it a metal? Is it H with F or N? Is it polar? Is it non-polar? Okay, that's why we spend so much time on this. It's really important that you know. Are the O's equal and opposite? So, it has to be London dispersion because it is a non-polar molecule. And I would absolutely use the moniker non-polar molecule. Okay, because we use non-polar to mean bonds or molecules, right? Be specific. Okay, so if you look under where it says London dispersion forces, okay, we've got to explain a little bit, just like we did with ionic, because now we're breaking ties. London dispersion forces depend on what two things? Number of electrons and, what did you say, Lauren? Size, space. Okay, it depends on size and number of electrons. Which one's bigger? Which one has more electrons? Lauren? CO2. Okay, so you're going to hate this statement, but it's going to save you with this type of London dispersion example. Okay, CO2 is what? Bigger. With more electrons. And is therefore more, what was the buzzword? Polarizability. So we're going to say more polarizable. Okay, that means we can shift the electrons wider or throughout the molecule, creating that stronger partial charge. Okay, and then has a, oh, shit. What was our property? What were we trying to identify here? We wanted lower melting point, right? Okay? So, should I use CO2 here? I probably should have explained it with neon, right? Where it has smaller, less electrons, right? So we got to fix it. CO2 is bigger with more electrons and is more polarizable. And therefore has stronger or higher IMFs. So then we can say neon, lower melting point. Okay, I probably should have done that differently on the back end. I apologize. So is this starting to make sense? Okay, understand, this is the basis for how things dissolve in solutions. Why things exist as they do in structures of solids, liquids, and gases. Why things react the way they do, okay, in thermochemistry. Why things go a specific rate in chemical kinetics. This is one of those paramount days, okay? Mark it on your calendar. October something something 2019. You will need to remember this day for an eternity until May. What's that? Is it the 9th? Okay. 10/9/19. The paramount day in AP chemistry for all of you. Write it down now. Okay. Now, okay, and I mean it when I say this is the explanation for so much of what happens, not just in chemistry, but outside the window. Okay, when you walk outside, this is why things do what they do. Okay? All right, do me a favor. Open your textbook or open your iPad to your textbook. We are looking for page 488. Okay, we're going to look at some of the chapter 10, like similar to your chapter 10 problem set. There's only 5 problems in chapter 10. Okay, but a lot of it is which one has the stronger force, which one has a higher melting point, and so on and so forth. Which problem? It's the damn day.
So next year, when we're in the world class in college, it'll pop up.
It's gonna pop up on your memories. Today was the damn day.
What the hell did I do?
Nothing. We're gonna be like, this wasn't important. I will tell you, it's important to this year. I can't promise you it's gonna be important for like 3 years on your timeline. All right, so I want to look at number 35. Okay, this is not one of your problem set. However, it is very similar to the 5 problems that you have in chapter 10. Okay, it says, predict which substance in each of the following pairs would have the greater intermolecular forces. So this one isn't necessarily tied to properties, it's just tied to the force. Okay, so letter A. We have CO2 versus OCS. All right, so looking at letter A, we know what CO2 looks like, right? What do we know about CO2? We said it was, Morgan, nonpolar, and therefore has, what's the only force that the only force of nonpolar molecules is London dispersion. Okay? Now, OCS, what do we know about S? Charge -2, it is sulfur. What group is it in? So who is it going to bond very similar to? Oxygen, right? So the molecule is going to look exactly the same, except for an O and an S. CO2 is nonpolar because we're equal and opposite, correct? What about OCS? It is a polar molecule. Okay, so now we should go through. We can go through the checklist, right? Is it a metal and a non-metal? No metals here, right? Is it one of the examples for network? Okay, is it a metal by itself? Is it H with F, O, or N? No. Is it a polar molecule? Yes. Therefore, polar molecules have dipole-dipole forces. That one is going to be your stronger force, simply because it typically does. Now, inevitably the question comes, are there molecules with London dispersion forces that have stronger forces than dipole-dipole? And the answer is yes, sometimes. Okay? Sometimes the number of electrons and just the sheer size can create a stronger instantaneous charge than ones that are there, that may be super small and have a super low number of electrons. That always, anytime you hear an always or a never, always be skeptical. In everything, not just chemistry, but especially here. Okay? This is a hierarchy for general trends. Okay? Think about ionization energy, right? The general trend from left to right was that it increased. Remember the two hiccups in the chart? Okay? It's a general trend. Okay? So there may be exceptions. All right. So if we look here, letter B has SeO2 versus SO2. Okay? Do me a favor, draw the structures. I'm hoping by now you remember SO2. We have used it at length. Oh my God. It's McRib season.
Yeah, freaking Maui is like.
Oh my God, have you ever had one? Oh. You know how they had the barbecue rib sandwich yesterday, Judd? The McRib is the real deal. Oh my God. Oh my. Has anybody not ever had a McRib from McDonald's? Oh my God.
McDonald's field trip right now.
McDonald's right now. Honestly, to hell with all of this. McDonald's field trip right now.
Is it really that good?
Do they DoorDash?
Yeah, they do.
to the high school.
Yeah. Are you kidding me? I have Pizza Hut. Like Pizza
Yeah,
Hut knows exactly where I
why
want
don't we do that anymore? Pizza Fridays, we used to do that all the time last
Just
year.
because lunch starts like
Yeah,
early,
right.
so like we would have to order it like the day before. So if you guys want to do it, we can do it.
Can we do it? Next Friday. Bring
What's today? Wednesday. There's a couple people not here, I think, Friday. Oh, you're not here, right? We won't do it to you on the table.
Next Friday.
Next Friday. Next Friday, pizza
Don't
lunch.
forget, Friday's taking over now.
Yeah, Pizza Hut knows exactly where I want everything. They bring it right to the back door. They usually text me when they get here. It's
Sorry,
kind of a
write a
thing.
reminder right now.
I'm not going to do that.
I'll do it.
I'll remind you.
Like
Like
five
$5 each,
bucks.
we'll get some breadsticks.
I cannot believe we have 4 dollars.
I know.
So, like, they have like, what is it, like a $5 menu? It's like $5 like medium pizzas or something like that. But we got like,
We got like 3.
yeah, we got like a bunch. We'll check. We'll look at price. Okay. So, did you draw your structures? They should look exactly the same. Why? S, E, and S, same group, bond the same way. Lauren Miller, what does your SO2 look like?
OO, S in the middle.
Okay.
Single bond. Fill out, single bond for both.
Okay.
And then fill the other one.
Yep.
And then 2 electrons in the middle.
2 electrons in the middle. Are you sure?
Oh, maybe not. Wait, is there 18 of them?
Well, so we got 18, right? 2, 4, 6, 8, 10, 12, 14, 16, 18. Everything's done, right?
No.
What's the last step?
S
S isn't satisfied yet. So we need 1. Doesn't matter where we take it from. Yes, but no. So what would this molecule exhibit? Resonance. Renaissance. Okay. So, all right, hold on. So your S, now granted, I forgot my dipoles. Now your SeO2 should look exactly the same way. Why? Because it's in the same group as S. Oops. So it's going to bond the same way. Okay, so is it a metal and a non-metal?
No.
Is it an example of network covalent? It's close, right? You said SiO2. SO2 not the same. Is it a metal by itself? Does it even have hydrogen in it? Is it polar?
Yes.
Is it equal and opposite? No, those are different, right? So it is a polar molecule. What do polar molecules do? Dipole-dipole forces. That means one of the negative ends is going to attach to one of the positive ends. All right, so SeO2, if it bonds the same way, what should the forces be? Forces should be the same. Uh-oh.
Never.
Now what?
I don't know. You tell
Sounds
me.
like sounds
Well, okay, so, all right, hold on. Whoa, don't just start yelling stuff. Can we use Coulomb's law? Why? Because it's not ionic. So what was the other tiebreaker?
Distance.
Polarizability, which means it has to be. What does polarizability mean? It's got to be what? Bigger with more electrons. So if we look, what's the only thing that's different here? Se is bigger with more electrons and is therefore more polarizable. So the stronger force would be with SeO2.
Let's go.
All right, C subs.
You don't have to do it.
No, you're gonna have to
Oh
do
my
it.
gosh.
Okay, it's honestly not that bad. It's just really big.
What in the monkey?
Listen. It's actually not that bad. It's just big. Okay. So if you look, it's a large macromolecule. The first one. Okay. Now this is a condensed organic formula. Okay. It says CH3, CH2, CH2. All that means is you have a C, 3 H's, and you connect to another C that has 2 H's. Another C that has 2 H's, and then what's that connected to? An N with what? 2 H's. Okay? Now, count your electrons. Okay, so how many electrons should we have? Lauren Haley. 26. Okay, here's how, listen, here's how you get it. Okay, carbon is 4 plus 4, 8 plus 4, 12 plus 5, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, how many have we used? How many have we used? 24, which means we got how many left? 2. Now, this isn't just a simple, micromolecule, right? We got to figure out who's not happy. Where can we put the pair? Nitrogen. Okay. So the next one is exactly the same, except what's different? They have the extra what? They have the extra N. So it tells us what order to go in. NH2, CH2, CH2, NH2. Right? However, check your electrons. If you think about what we did in the first one, the second one should be pretty easy to fix. Where do we need electrons, Tyler? Both sides of the end. Okay. All right, here we go. So, John, is it ionic? Why? Both of them. Are either one ionic? No. Why? Because there's no metal. No, right. There's no metal plus a non-metal. Good. Asher Plenty. Is it one of the examples of network covalent?
No.
Nope. Morgan. Is it a metal by itself or an alloy? No. Clayton. Is it a hydrogen bond? Why?
Well, it's not because.
What? What is a hydrogen bond?
Has
H connected to
FO.
F over N. Do we have that somewhere? Sure. Right? So the first one, we have a non-polar end here, right? But this section is capable of hydrogen bonding. How about the second one? Chase, what do you think? Yes, what? True. It is capable of hydrogen bonding on both sides. Okay, so remember, we can have polar molecules, but if they hydrogen bond, that takes precedent. That trumps the dipole forces. We can have London forces. If it can do something stronger, that overshadows the weaker force. So, which one is going to be stronger? What would your expectation be, Garrett? You're thinking about it?
Yep.
It's dangerous when you think.
Good job.
Why would you say the bottom? Okay, so how would you say that? If I was asking you this on a college board exam, why, logically, what is this capable of? I wouldn't number it, but I would say it's capable of more hydrogen bonding. okay? Because this one has to only be oriented such that this part connects, right? Whereas this part, you have multiple opportunities to hydrogen bond. Does that make sense? Okay? All right. Are we okay? Like I said, this is a very, very important concept, and I really want to drive it home through your heart. Like a steak, you vampires.
Halloween!
Happy Halloween. Okay, so look, in your textbook, okay, 33, 34, I think it's 37,
That's
38, and 40, I forget exactly. Hold on.
Wait, I haven't written
There's
down.
only 5.
Very
It is 33, 34, 37, 39, and 40. Okay? So it's a lot. Okay, so for example, now I want you to look at 39. Okay? When we talk about highest boiling point, what kind of forces are we looking for? Tyler, highest boiling point is what kind of forces? Strongest or weakest? Strongest. Okay? Highest freezing point. Strongest or weakest? Highest freezing point. Strongest. That means it takes the most. Okay, remember, what point is the same as the freezing point? What point is exactly the same temperature as a freezing point? Melting point. Okay? So, if it takes more heat to melt it, okay, stronger force. Okay? Look at where it says vapor pressure. Okay? Because this one we didn't talk about really much yet. Okay? Now, here's what vapor pressure is. So I want you to understand a little bit about it before you can rank it. Okay? Vapor pressure is when you have a liquid. Okay? And now, this is a bad example here because it's superhuman, right? Okay? But over the course of a couple of days, your samples from lab should evaporate. Okay? Now, not all of them have done a great job so far. Okay? But hopefully this is less volume than what you started with. How that happens, because it's not, can we agree it's not going to get to over 100 degrees in here? Okay? So it's got to happen another way. It has to do with the difference between atmospheric pressure that pushes down on the particles and vapor pressure that the particles at the surface push up with. Okay? So these particles at the very edge of the surface are trying to escape. If they have more pressure, so if the vapor pressure is greater than the atmospheric pressure, then they escape to become a gas. If the vapor pressure is less than the atmospheric pressure, they stay as a liquid. Okay, they get pushed down. Now, vapor pressure means they're trying to escape more. If they want to escape more, is that higher intermolecular forces or less? It's less. If they want to get out of the liquid phase into the gas phase, higher vapor pressure means lower intermolecular forces. Okay? So then D says lowest freezing point, lowest boiling point. Those are weak. Okay, the other one I think that comes up is what's called viscosity. Okay, number 40. Anybody know what viscosity is? Right, it's the thickness of a fluid. Okay, can you think of a thick fluid? Toothpaste, if you call that a fluid? Molasses is a really good one. Motor oil. Okay, think about how liquid, like how water pours versus like a molasses or like a really thick syrup, right? The thicker it is, stronger the force. So high viscosity means higher forces. That's why it's so thick. It has a hard time separating from the other particles. Okay? The other ones there talk about heat of vaporization. And then F says enthalpy of fusion. Enthalpy is another word for heat. So basically E is how much heat it takes to vaporize. F is how much heat it takes to melt. Fusion is melting. Okay, so E would be highest force. F would be lowest force. Okay, so what, if you remember when I had Clayton and Garrett up here, and I started shaking them more, the more I shook them would be more heat. Okay, so the more I had to shake to separate them, that means you would need a higher heat of vaporization or a higher heat of fusion. Okay, that is it for this unit. Tomorrow essentially becomes a work day. Friday, we're going to kind of tie all this back together and give kind of like a little review activity. And then we'll start with presentations, online quiz, exam. I'm thinking probably like Thursday next week. Right? If I had to guess. Lab books are like Tuesday, Wednesday-ish. Yeah. And I'm a little bit lenient there, you know, if you need a little bit extra time. Presentations will probably be Tuesday. Online quiz when, like I'm thinking sequence-wise, you know, review on Friday, workday Monday, presentations Tuesday, online quiz due Wednesday, test Thursday. Okay, that's kind of how it goes. Okay, if we need an extra day, then we get an extra day. Okay. All right, you've got the last like 10 minutes here if you want to get a start on something, if you want to ask something. If I lost you at some point today, please be found soon.
What did you say?
I said if I lost you at some point today, please be found soon. And whether that means talking to me or somebody else, okay, please, please, please make sure today comes home. Most slippery.
I'm not saying I'm not gonna get it.
Wait, what was that?
I forgot
And it sounded like, oh, I don't remember.
Is that yours or is that yours?
It's like,
Is
what
that
do we
you're
do
talking about?
now?
Was that flows the
Oh,
easiest?
Yeah, so like what is most,
Flowy.
most gaseous liquid?
Most gaseous.
I don't think that's how you say that. I thought it was gaseous.